In our last class we were discussing some of the grid routing algorithms. If you recall, we had started our discussion on the maze running or maze routing algorithms. We had talked about one of the very popular and classical algorithms, namely the Lee's algorithm. And if you recall how the classical Lee's algorithm operated, it started from a given source and it proceeded with labeling the neighborhood grid cells in a breadth first fashion. So, since it is proceeding in a breadth first fashion, the idea behind Lee's algorithm is that if a path exists from a source to the destination, you will always find it. But one drawback of Lee's algorithm was that it was more like a blind search. Well, there we were not giving any emphasis on approximately in which direction the target cell is located. So, the cells were labeled in all possible directions, but finally when we touch the destination we have found out a path. So, we have also looked at some of the improvements of Lee's algorithm in terms of reducing the memory, number of cells you need to label, like the order in which you start the process, which is the source, which is destination, or you can start from both directions, or you can have an imaginary bounding box and limit. Also the numbering process, instead of numbering them as 1, 2, 3, 4, I had talked about a scheme where you can alternately label these cells as 0, 0, 1, 1 and so on. Okay. So, today we will be talking about an algorithm which is similar to Lee's algorithm in the sense that it also works on a grid, it also labels the cells, but it is more of a goal directed method. It tries to take advantage of the fact that which direction the final target is located. Now, this algorithm is called Headlocks algorithm due to the person who initially proposed it. Now, in Headlocks algorithm there is a concept of detour numbers, and we actually label the cells not by its distance from the source, but by the so called detour numbers. Now, as I just mentioned, this is a goal directed search method. From a source we somehow try to find out which direction the target is located. Now, the detour number, the definition, the way the detour number is defined, it is defined with respect to a path. Suppose I have a source here, I have a target here. Suppose I have a path like this, it is going towards the target, then moving in this direction like this. Detour number is defined as the number of grid cells which are directed away from its target, because if you take this simple example, in the best case we could have connected S and T by a straight line, that is the best case, but maybe some obstacles are here in between. Okay. Suppose to overcome this obstacle we have to move away in this direction, say 3 grid cells. So, when we come back here we again have to come back 3 grid cells to reach the target. So, detour number is an estimate of how far away we are moving away from the target. So, it is the number of grid cells directed away from the target, and it is defined with respect to a given path. Now, if dp denote the detour number, which is the number of cells we are moving away, then the total length of this path will obviously be this, the best possible path, which is the Manhattan distance, plus twice of the detour number. The number of cells you move away will be the number of cells you will again have to come back. Okay. So, this is how you can estimate the length, and this is how you can use the detour number. Okay. Now, using detour number we can modify the cell filling phase of the Lee's algorithm like this. See, in case of Lee's algorithm we started with the number 1, then 1, 2, 3, 4, in that way we proceeded in a breadth first fashion. But in this algorithm what we will try to do, starting from a given source, we will always try to move towards a direction which will give us a lower value of detour number. the cells which are labeled with a lower value of detour number, those are the more desirable paths to the destination possibly. So, here also we are doing some kind of a breadth first search, but it is a goal directed search. We are not doing a blind depth first search, we are labeling the cells by detour numbers, not by their distances from the source. Okay. So, the cells are filled with the detour number with respect to the given target, and the way we expand the cells or label the cells is we always take the smaller detour numbers as the cells with higher priority. So, if a cell is labeled with a smaller detour number, say 1, and another cell is labeled with 2, we will be expanding this cell first. But as you will see, I will give an example that retracing of the path will be slightly more complex as compared to the Lee's algorithm, and you need some kind of a search to do that. So, let us take an example to illustrate the detours algorithm. Okay, so this is an example grid we take. This is the given source and this is the target to which we need to connect. First is that we observe that the target is to the right and to the top of S. So, the desirable paths will be either the paths which are going to the right or going to the top, but the top paths are blocked to the obstacles. So, only we have this one cell which will have a detour number of 0. Detour number 0 means we are not moving away from the target. The rest all will be having a detour number of 1 because we will have to move away from the target. Similarly, this is the cell we labeled in the first step. In the next step again you see the neighbors of 0. There is another cell we will find out that is also will be having a detour number of 0 because still we are moving in the same direction. But now the problem arises, we cannot move in any other direction with the same detour number. So, we will have to move out. So, now the different choices are 1, 1, 1 and 1. These are the detour number 1 because we are moving away from the target. Now, the next step we will be expanding all the remaining cells once. So, if we expand in this direction, this will be again be moving away, this will become 2, this will also become 2, this will become 2, this will also become 2. For this one, the left cell is also you are moving away 2, but when you move up you are not moving away. So, this will be 1. So, now these 2's will be the cells of lower priority, you take the cell with a lower number, this one. So, try to expand this first. So, you are moving away, label it as 2, this will be 1, you are moving in the direction of the target. So, you continue this process. For this one, here you are moving away, here you are moving in the right direction, here also you are moving in the right direction. Similarly, for these ones, here you are moving away, here in the right direction, here in the right direction, above also. Similarly, you continue this process, this will be 2, this will be 1, this will be 1, in the next step again you expand this will be 1, this will be 1, this will continue, this will be 1, this will be 1, in the next step this will be 1, this will be 1, this will be 2. Oh sorry, this was 2, right, this will be 2 because here you are moving away, right, you are right. This will be 3, fine. So, now you are moving away from the target because you have reached the row of the target, you are moving up. So, from okay, now you have so many cells which are labeled 2. So, this all these cells are candidate for expansion. So, for this 2 you labeled it with, you make it 3, for this 2 this will be 3, 3, 3, this all will be 3 because you are moving away. So, now the lowest number ones are 3. So, now you will have to expand the 3's. So, if you move here this will become 4, this will become 4, this will be 3, this will all be 4's. This will be 3, this will be 3, this will be 3, this will be 4, this will be 3, this will be 3, you finally reach the target. So, this is the essential idea behind Headlocks algorithm. Well, you just label the cells by the detour numbers and you always take the lower detour numbers to explode in that direction. So, you are always trying to explode in the direction of the target. This is a very simple example I have taken, but for more complex examples, the number of cells you need to expand is typically much less as compared to Lee's algorithm. But of course, in this example you cannot appreciate that really, but for more complex examples you will see that the number of cells that are getting expanded are much less. But if you look at this example, you will find that retracing of the path is not that easy. Well, one thing you know, that if the neighboring cells of the target is marked as 3, then you will have to retrace a path where the labels will be in the descending order. First some cells mark 3, then some cells mark 2, then some 1s, finally to the source. This will be more like some kind of searching is required for this process, and this searching is not trivial. I just suggest that you try to find out a scheme or an algorithm to retrace a path from the target back to the source. Retracing is not as trivial as in case of Lee's algorithm. Okay. Now, as I said that the number of grid cells filled up is considerably less as compared to Lee's, but running time though it is less as compared to Lee's algorithm in general, but in the worst case this can also go up to n square for an n by n grid. And so, the worst case complexity is not reducing, it really depends on the obstructions and also the locations of S and T. Okay. Now, these maze running algorithms have the advantage that if you have a path existing between the source and the destination, this will find the path. But the problem is that the memory requirement and the computational time overheads are pretty high. So, there are some alternate algorithms which have been suggested where the information is not kept or maintained in the form of a grid of cells, rather as some geometric shapes and some lines. These are called the so called line search algorithms. Now, here let me tell you, in the line search algorithms we are not trying to reduce the time and space complexity both. In fact, we will see that we can reduce the space complexity drastically, but the time complexity really does not decrease much. Now, in case of line search algorithm, the basic idea is that, well, to start with, assume there are no obstacles. Suppose you have a source out here, you have a target out here. The idea is that if you draw a vertical line through S, an imaginary vertical line through S and an imaginary horizontal line through T, they will intersect at some point. So, if you trace back from the point of intersection back towards T and S, you have found out the Manhattan path. Now, in the absence of obstacles, only one such horizontal and vertical line will be able to find the path. But if there are obstacles in between, you may have to trace a number of such straight line paths, and you will have to keep track a number of such line intersections, and you will have to trace those intersections to get a set of straight line segments. Now, the idea is that we are not maintaining the information about the grids and the obstacles as an array like in Lee's or Headlocks algorithm. Rather, we are maintaining the exact coordinates and the shapes of the obstacles and also the coordinates of the source and the destination. Now, the basic data structure we will be using here is some kind of you can say straight lines. We will be storing information about straight lines, and the processes will involve that whether two straight lines are intersecting, whether a straight line and a given geometrical obstacle, a rectangular block typically, they are intersecting, and so on. But a point to note is that these line search algorithm always do not guarantee the optimal path. Well, you may find a path, but that may not be the best possible one, because you are always trying to find out the longest straight line segments and intersecting them and finding out, but there can be some shorter paths with a lot number of bends. So here the number of bends in the wires are typically less. Okay. So may need several backtrackings in the presence of obstacles. While the running time and memory requirements are significantly less, in fact memory requirements is drastically low, as we will see, and the routing paths which you finally find out is represented by a set of line segments. So from source maybe you will get a path like this and some straight line segments. But you can compare this with Lee's or Headlocks algorithm, where finally the routing information you get in the form of a matrix. From the matrix you will have to deduce back and determine the path. Okay. Now under the line search algorithm we will be discussing two different algorithms. First is an algorithm due to Mikami and Tabuchi, then we will talk about an improvement of this. Mikami-Tabuchi's algorithm is fairly simple in concept. This says that S and T are the pair of terminals you want to connect. Step 1 is generate 4 lines, 2 horizontal and 2 vertical passing through S and T. Suppose this is S and this is T. To start with, you pass a horizontal and vertical line through S and a horizontal and vertical line through T. These are the 4 lines. Now these lines will extend in all directions till they hit the floor plan boundary or an obstacle. So these will be extending till they hit obstructions or the boundary. Now if a line which is starting from T intersects with a line starting from S, we have found out the path. But if not, these set of lines we have started with, they are identified as trial lines. Well, initially they are of level 0, then there will be level 1, 2, 3 will go on. These are the trial lines. Now the trial lines we keep in some kind of a list or a queue for further processing. This is the data structure we are maintaining. We are keeping information about these lines, right. Now in general, in step I of the iteration, we pick up the trial lines of level I. See, at step I, the trial lines of level I minus 1 have all been taken care of. Okay. So we pick up the trial lines from the list or queue, whatever you call. Now along the trial line, all the grid points are traced. For example, this is a trial line. Now here, although we do not have explicitly the grid structure, but we can identify the grid locations along this line. Suppose these are the grid locations. So along the trial lines, all the grid points are traced, and from this grid points new trial lines are generated which are perpendicular to this line. So trial lines like these will be generated, which will be perpendicular to the trial line from where you are exploring. Now you continue this process. Now if a trial line of some particular levels I plus 1 intersects a trial line from the other terminal point, maybe at level I plus 1 or less, then we have found out a path. So just by tracing back the intersections, we can find out the path. Now this algorithm will guarantee to find a path if it exists, but not necessarily the minimum one, as I mentioned. So let us take an example and illustrate it so that it will be clear that how it works. So let us take an example like this. This is the boundary, these are the 2 obstacles, this is the source and this is the target. So to start with, there is a horizontal trial line like this and a vertical trial line like this. So we start from S. Similarly from the target, These are the two trial lines. Well, at the next iteration, we will have to, these are the trial lines of level 0. So, we will have to identify the grid point. Suppose this is a grid point, this is a grid point, this is a grid point, and these are all grid points, suppose. So, we will have to trace trial lines along all these grid points in the next iteration. Now, in fact, in this example, here itself you will get an intersection. So, from S, trial line of level 1 is intersecting a trial line of level 0 from T. So, if you get that from here, you can systematically backtrack and will get the path like this. This will be your path. But if there are more obstacles, you may have to generate some more such tracing paths. Now, this is the essential idea behind the Mikami-Tabuchi algorithm. But one thing you just try to understand, that in this algorithm, the number of trial lines you generate may be pretty large, because along each line there are so many grid points. But intuitively you see that all these lines are not really useful lines, because say with respect to these, you will see many of them are anyway, they are hitting this obstacle. So, just along this line you cannot go much further, but rather if you can identify those lines which can just extend beyond the obstacles, those will be the useful ones. Okay. So, the next improvement of this algorithm, it tries to utilize this fact to make it more efficient. This is called the Hightowers algorithm. This will not guarantee optimal path. Just as I told you, it tries to just trace the straight lines and try to find out the longest straight line intersections, but there can be a shorter path with lot of bends that you will find in more number of iterations. See here, number of iterations is equal to the number of bend, you can see. So, there can be a path with less number of bends, but the path length may be long, number of bends may be, but the shortest path may have a large number of bends. So, the number of iterations you will need to detect that path will be more. Okay, so in case of Hightowers algorithm, well, as I told you, this is similar in concept to Mikami-Tabuchi in the sense that here also you are throwing lines along horizontal and vertical directions, but you are not generating all line segments perpendicular to a trial line with respect to the grid positions, but rather we are only generating a few of the interesting lines. Given a trial line, we find out only certain interesting grid positions and we generate only trial lines perpendicular at those positions, not in all grid positions like in Mikami-Tabuchi's algorithm. So, the idea behind these interesting grid points is that the new lines should be able to bypass the obstacles which are lying in between. Now, bypassing these obstacles, there is a concept of escape point and escape line. You are trying to find out, suppose here we had an obstacle. So, you try to find out that which is the best point you should choose so that you can escape out of this obstacle. This point will be called an escape point and the corresponding trace line, trial line will be called an escape line. Okay. So, steps of the algorithm are similar to Mikami-Tabuchi's. You pass a horizontal vertical line through source and target to start with. So, if they meet, you have found out a path. Well, otherwise you pass a perpendicular line to the previous probe whenever it intersects an obstacle, but here you use the concept of escape point and escape line. Not means here you are not considering all possible grid points and the lines emanating from them. Okay. This is the main difference. So, just if you take yes.
In this case, there will be two like such points, one on the right, one on the left.
There can be more also. Let's just take the example and try to find out. Let's take the same example. These are the first level probes, the horizontal and the vertical lines. Okay. Now the horizontal and vertical lines will be hitting the boundary or the obstacles. Well, the boundaries we are not concerned for the timing, we are more concerned with the obstacles. So you look at this line is hitting the obstacle. So you trace along this line and find out exactly at which point on this line you can come out of the obstacle. It is a point out here. It is a point out here where you can escape out like this. Similarly, for this trial line, the escape point will be here, that you can just come out of the obstacle. Similarly, with respect to these, for this obstacle, the escape for this line, the escape points will be here and here. So there will be one trial line like this, another trial line like this. So in this is how you are trying to find out you can say the escape points. You will have to search the obstacle, reach the obstacle boundary, just the first point beyond that will be your escape point. Now in this way you go on tracing and find out the first intersection of a line from here and the line from here. In fact, you have already got the path which you had earlier obtained, this one. This will be the first path you will get.
Should we expand only those lines which hit the obstacle, and what about those?
See, we only expand those lines which hit the obstacle, because other lines mean what? The other lines are already extended along its length. If there is an intersection, they will intersect anyway. So we need not worry about the other lines. They have been explored to the maximum possible extent. But the other lines were hitting the obstacle. Maybe if you go away, just means outside the obstacle, you will find a path, a new path.
So then, for example, this vertical line, so this is not hitting any of the obstacles on T.
On T, yes.
Still you found an escape point for this.
This is not hitting an obstacle, but we are identifying the escape point, because when we take this as a trial line, we will have to find out the escape point. When we are trying to draw say lines perpendicular to this, then we will come to know that there is an obstacle and we find out the escape points. Yes, 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 yes. Here whether it hits or not, we will have to search and find out the escape points. Now the main idea behind this algorithm is that the memory requirement is drastically reduced, but computational time is not really reduced much, because you have to make a lot of searching in order to find these escape points and keep track of these escape lines and the intersections. So the running time does not decrease appreciably, but the memory requirements get reduced drastically. Okay. So this is one advantage of this kind of line search methods. Okay. Just to mention, there are a number of algorithms which specifically talk about Steiner trees, because ultimately when you lay out a net on a surface, it is a Steiner tree we are trying to draw, because a Steiner tree, if you recall, they will have the connection segments as horizontal and vertical lines, and there can be some intersection point like here and here which are not one of the terminal points. So some algorithms try to find out, well, determining the best or minimum cost Steiner tree is an NP complete problem. So there are algorithms to find out a good Steiner tree connecting a set of points. See, the maze running or the line search algorithms that we have discussed, they are basically used to connect a pair of points at a time. But a Steiner tree kind of algorithm, they can take a set of points, a net list, a net, and they will try to construct a Steiner tree usually connecting all these points. So, they look at the problem slightly more globally. So, the minimum Steiner tree, as I had mentioned, it is an NP hard problem. So, you never try and go for the minimum possible solution. Now, with respect to Steiner tree based algorithms, I am not going into detail, I am just mentioning that there are several classes of such algorithms which have been proposed. Well, one is the minimum length Steiner tree. Of course, this is an NP hard problem I have just mentioned. The goal is to minimize the sum of the lengths of the edges of the tree. So, exact versions exist, but the running times are large. There are approximate versions using some heuristics which give fairly good results. Many commercial routers use them in fact. Well, the Steiner tree may have some weights, like say a tree, when you have when you have a number of terminals to be connected, suppose this Steiner tree is like this is the best Steiner tree. But with respect to the layout area, these segments may have to pass through different routing regions with respect to the floor plan. Now, these different routing regions may be having different costs with respect to the area available for routing. So, accordingly you can define some weights of the different edges of the Steiner tree. So, in that respect you can even talk about weighted Steiner tree and try to minimize the cost of the tree. The length is L and the weight is W. So, the cost of that edge will be L into W. So, in weighted Steiner tree you also take into account the congestion in the individual segments of the line through which routing regions you are actually taking those lines through. In fact, some of the modern tools also consider such Steiner trees with non-rectilinear edges which are angled at 45 degree or minus 45 degree. So, there you can have some interconnecting lines like this, you can have a line connecting like this, another line connecting like this, another line connecting like this. So, lines at an angle of 45 degree are also allowed there. But as you can understand, the problem becomes much more complex here, but some CAD tools do use them. Okay. So, actually we have looked at some of the grid routing algorithms basically, where the layout, the obstacles and the already routed nets, they are expressed in the form of a grid. Well, the grids you can represent either by a matrix or by some geometric information like lines and some rectangles. Now, we had looked at a small sub problem of routing. This grid routing, whatever we have looked at, that is just a set of algorithms which we use to connect a set of points, a pair of points typically. But now let us look at the routing problem from a slightly more global perspective. Then we will see later how these algorithms we have just discussed, they fit into the total picture. Okay. So, we now look at something called global routing. Global routing means we are looking at the routing problem globally. We have the whole chip surface, we have all the obstacles, we have all the nets which are to be routed. So, now we have to make a plan that how we will be routing these nets. There can be 1000 nets for example. So, how we will be routing these 1000 nets, in what order, through which areas we will have to route the net, because we cannot use a maze running algorithm to route all these nets, because the chip area may be quite huge. There may be nets which may be running from one corner of the chip to the other corner. So, just using those algorithms in a chip may be too costly. We will have to do some kind of a divide and conquer strategy. Okay. So, in practice the routing problem is solved in two steps. The first step which we are discussing now, that is called global routing, which will be followed by another step called detailed routing. Now, in global routing what we do? We define the so called routing regions, because ultimately in the chip after placement we have the blocks placed in certain locations. Of course, there is some space left between the blocks. So, we will have to define the routing regions and their relationship among themselves. With respect to the routing regions we have defined, we will have to generate a tentative route for each net. This is tentative, this is not the exact. For instance, on the silicon floor, suppose I have a block like this, I have a block like this, I have a block like this. So, these will be the routing regions. Okay? This is one routing region, this is one routing region, these are all routing regions. So, if we have to connect a pin say from here to a pin say out here, then we will have to find out the sequence of routing regions through which this net has to be routed. For example, I can say you first come here, then come here, then come here, then come here. So, we specify a sequence of routing regions for the net, but we do not specify the exact geometric layout of the wires as yet. We just give a tentative route that this is the path you will take. Now, each net, as I said, is assigned to a set of routing regions like this, but this global routing does not specify the actual layout of the wires. That is done only in the second step. After this rough routing information is generated, then you consider one region at a time and try to complete the exact layout of that region. For each routing region, each net which are passing through it is assigned particular routing tracks, which means you are assigning exact geometric locations for those nets. So, after detailed routing, the actual layout of the wires will get fixed. Okay. Now, we will see later that for this detailed routing, there are two sub problems which come up. One is called channel routing and the other is called switch box routing. And in fact, all the most common detailed routing sub problems can be mapped into either channel routing or switch box routing. Okay. First, let us look at the problem of global routing. Okay. So, first let us talk about the so called routing regions. I just mentioned the routing regions are the areas which are left between the blocks during placement. They are the regions through which the interconnection wires have to be passed. Now, the problem is that how do we define these regions? Well, it is not difficult. You can partition the total routing area available to you into a set of non-intersecting rectangular regions. Like suppose you have blocks laid out like this, then you can say that, well, this will be one region, this will be one region, this will be one region, this will be one, all will be rectangular in shapes. Okay. Now, with respect to the geometry of these blocks and the associated regions, routing regions can appear in one of these three types. Well, horizontal channel means, well, the name horizontal means it is parallel to the x axis. It says that the channel is like this with some points which you want to connect on top and some points on the bottom boundary. You will have to connect some of the points from the top to some of the points from the bottom. Maybe you will have to connect a wire like this, connect another wire like this, and so on. This is horizontal channel, and if you rotate it by 90 degree, it becomes a vertical channel. So that the pins are located to the left and right. and it is parallel to the y axis. But in some cases the problem becomes more complex and we get something called a switch box. A switch box is a channel where pins are located on all four sides and you will have to interconnect them. So, the routing area is of course rectangular in shape, but pins are available on all four sides. This is called a switch box. So, a routing region can be either some kind of a channel or a switch box. Now, before we actually start the process of global routing, this identification of routing regions is extremely important. And in most design style, of course, we are not talking about FPGAs and gate arrays. Well, other than FPGAs and gate arrays, routing regions do not have prefixed capacities, because if you see later that while the space becomes a little less for routing, I can always shift the block ups to make a little more space. Like in standard cell, there are some rows of cells with some space in between some routing. So, if I find that the space is not sufficient, I can always shift the rows up to make more space. So, the routing regions, they do not have prefixed capacities, but it is important to determine some kind of an order in which the routing regions have to be considered during detailed routing, because the order in which you take up the regions for detailed routing, that will play a significant role finally in determining the quality of the layout. Okay, this will take some examples and show you later. Okay. So, these are related to the routing regions. Now, also let us talk about something called channel junctions. Well, in a typical layout, switch boxes are rare, but there will be switch boxes in some places, you cannot avoid, but channels are much more frequent. So, we will be getting mostly the channels. So, when you have channels, you will have intersection or connection between channels. Broadly, you can have three kinds of channel junctions. One is the L type channel junctions, which can occur near the corners of the layout surface. Like I have an illustrative example slide. Say here, suppose this is a layout and there is a block near the corner. This is a layout channel. From here you may want to route some nets. This has a shape of a L, right. So, this occurs near the corners. Well, for L type channels, ordering is not important. This you can take up in any order, because in an L type channel, the other channels do not interfere much with this channel. This is near the boundary, okay. And you can use the conventional channel routers to handle L type channels also. How? Suppose you have an L type channel here, you can break it up into two channels like this. You can have one channel like this, you can have another channel like this. So, you can treat each of them as individual channels and you can route them using channel routers individually. So, L type channels do not create much of a problem in terms of ordering. T type channel is the second type, where the channel between several blocks has the shape of a T, like the example here. There are 3 blocks and you have a T out here. The space you have in between has the shape of a T. Okay. Now, if we have a T type, okay, here we are basically calling it a channel, but our definition of a channel is the pins are only at the top of the bottom. So, here we are using channel for to express that it is a routing area. Okay. But this T type channel also can be routed using conventional channel routers. How? See, if we have a channel like this, then we impose an ordering. What we say is that we will be routing this particular channel first. The leg of the T we handle first. Because I will tell you, well, if you handle this leg first, there will be some pins on this side, there will be some pins on the other side. So, you will have to interconnect them. Well, moreover, there can be some pins out here also, but on this boundary, the position of the pins are not fixed. Those are so called floating terminals. So, as this channel routing is completed, those nets which are going out of this, they will get assigned some fixed points on these boundaries. Now, after these points have been fixed up, this becomes more like a conventional channel. But if you do it the other way around, you will be in problem. You cannot treat this as a whole channel with a hole in between. It becomes more difficult to handle. So, the leg of the T is handled first, then the shoulder. Okay. But the more complex kind of channel have a shape like a plus, where you will have switch boxes. You will require switch box routers, which are typically much more complex as compared to channel routers. So, an example like this. So, if you have something like this, then well, you can have a channel out here, you can have a channel out here, similarly a channel here and a channel here, but this space in between, this will be a switch box. This will be a switch box, because here pins will be coming from all four sides, right. So, here you cannot do away with switch box routing. So, a heuristic says that during placement you place them in such a way that this kind of plus type junctions are avoided. Okay. So, you better move the blocks around, and so that you get T type junctions is fine, convert plus type into T types wherever possible. Okay. Now, finally, some design style specific issues. Well, if you have a full custom design style, then all the problems we have just mentioned, all of them apply. There are all kind of channel junctions, as we have mentioned, can apply. Blocks can be of all possible shapes, and moreover here the channel capacities are not fixed, the channels can be expanded, and some violation of capacity constraints are allowed, because we can expand the channels. But one thing to remember, well, although we are saying that we can handle expansion of channels if required, but if there is a major violation, we see that the space we have kept, we have to double that space, then basically what we are talking about is that we are making a drastic change in the placement by shifting the blocks up considerably. Maybe if we go back to the placement and redo it, it will be better. So, normally during routing, well, we allow some violation of capacity constraints, but not drastically. So, if there is a major violation, then typically we may have to go back to the placement, just address this problem, again come back. Okay. But if you have standard cells, for example, standard cells, if you recall, there the cells are all of the same height, they are all placed along some of the rows. Now, I had mentioned earlier also that in standard cells there are some special cells available in the library. These are called feed through cells. Feed through cells do not do any computation, they just connect a pin on the top to a pin on the bottom. For example, in here this represents a feed through cell, this is another feed through cell. So, a feed through cell is used to connect across channels. So, when you are doing a placement, then the placement tool will know that how many nets are crossing the channels. So, accordingly the feed through cells are inserted. The placement tool will know that how, suppose it says that there are 2 wires that are crossing these 2 channels. So, there will be 2 feed throughs which are inserted. Okay. So, in standard cell design style, after the placement, location of each cell gets fixed. Not only that, feed throughs also get fixed, the capacities and also their exact location. But if during routing you find that due to some reason the placement tool made a miscalculation, the number of feed, for example here, if these 2 feed throughs have already been occupied by some nets and you need to connect A to B, so here you do not have any path of connecting. So, you will have to insert a new feed through cell. So, here if you have insufficient number of feed throughs, this may lead to failure in the interconnection. So, the placement tool must be careful enough to insert sufficient number of feed throughs. Of course, it is not a very difficult problem, you can just analyze the netlist and you can find out. Yes.
So, can we add one more feed through, like when we found in the routing step that we need one more feed through?
See, at the placement stage it is easy, because at the routing stage, see, you are carrying out routing and at some point you find that the feed through is less. So, if you try to insert a new feed through here, then everything on the right will have to be shifted. So, what you can do, you will have to undo all the routing you have done and then insert it and then again redo it. Because if already some routing you have done, if you shift a part of it, well, it will also carry all the wires along with it. So, the topology of the interconnection means it may become very inefficient if you just drag it like that. So, well, you can insert, but you will have to redo the routing of the corresponding channel after you do that. And we will see that there is another new technique which has come up since the last few years. This is called over the cell routing. This says that you utilize not only the space between channel, but also the space above the cells for interconnecting some of the pins. So, if you utilize this space above the pins, then the amount of space you require between them becomes much less. So, you can virtually get a channel-less design. So, the channel size becomes insignificantly less.
So, how is the channel heights are not fixed?
Channel heights?
Is always the same as why are they not?
No, in standard cell there is no reason why they are fixed, that you can move around. Only thing you are specifying that which cell you are placing along which row, because in standard cell there is nothing which are already prefabricated, everything you are fabricating. Those you can move around. And finally, in case of gate array, the size and locations of the cells are fixed, the routing channel and their capacities are also fixed, how much space you have. So, placement and routing must go hand in hand. Suppose there are 2 routing rows between the cells and you have already connected like this. Now, you need a connection like this. This you cannot do. So, you will have to change the placement and you will have to again redo it. So, for a gate array, the main criteria is typically to guarantee routability, whether it can be routed within the available limited resource or not. Well, there are issues like critical paths and other things, they also will have to be addressed, but routability is most important there. Okay, so we had looked at some of the basic problems in global routing. Now, in our next class, we will be looking into the global routing problem in some more detail, and we will talk about exactly how the global router tries to find out the regions for each individual nets. So, thank you.